Thank you for coming, and I'm very excited to give this talk. It's not often I get asked to give a talk about my opinions, because I always give my opinions, and people get very bored with that, I think. That's part of the reason. But this is such a vital topic, and I hope by the end of this talk, I can convince you that there are two great challenges we have as scientists. One is energy, and one is the effects of energy, which are climate, and that we need some sort of sense of balance in these. We both need the technologies of energy, but we also need some way to mitigate some of the effects. So I also want to show you some developments, very exciting developments in energy, and alert you to something that is very pressing, something that called a threshold in our climate system that we also need to be aware of. So I'm going to be talking about carbon, and I'm going to begin this talk with some slides that date back from time just to provide some kind of framework of these paired issues, energy and climate. So going back to 1987, Time magazine was already featuring the greenhouse, and we're still discussing whether there is any threat of climate change, at least in the Australian. I often see arguments that climate isn't really significantly changing, but going back to 1987, we already see that and an evolution of that issue to the war on global warming. In 1939, the French find wealth in the desert, and we see the trajectory of issues ending up life in hell associated with cheap hydrocarbons. Together, these two issues have reigned supreme in some of the most important policies countries have made recently. And they're linked, they're intimately associated. I'm not going to talk a lot about chemistry in this talk, but I think it's important to think about this simple equation of photosynthesis, because this is where these two things come together. So carbon dioxide from the atmosphere mixing with water produces leaf material, organic material, CH2, and oxygen. Now, if you're not very comfortable with a chemical equation, we can look at it this way. Carbon dioxide from the atmosphere and the sun's energy, electrons plus water, produce carbohydrate, which is really the leaf, and oxygen. Okay, so two very important things. Here is the source of the energy we utilize. It's really the sun, but it's stored within the leaf. And it also produces oxygen, which supports us. That's the oxygen we breathe as animals. The back reaction, of course, is if we burn this thing, we reproduce that energy and reproduce that carbon dioxide. So we run this equation backwards, and this is the reaction that our bodies are undergoing right now, producing carbon dioxide. And this is the same reaction your automobile utilizes to produce energy. So you may be wondering what this thing is that we have up here. You're all part of a scientific experiment, or a scientific-like experiment at the moment. This is a new piece of equipment we have purchased I'll talk about in a minute. It's monitoring the CO2 in this room. It's trying to identify how much CO2 we're producing by this back reaction and how much is accumulating in this room. So it started out about base level, 380 ppm, which is outside. And it has grown very rapidly as you've come in, and I'll feature this in a moment, to about 780 ppm. These are the concentrations of CO2 in the atmosphere of Earth during very warm periods of time. And the air is coming in through this tube, and it's going into this instrument. And you can watch it as it changes through this talk. And maybe there are moments when things get really exciting, and you'll see a big peak in CO2. It's also monitoring methane, so I warn you. It's interesting if you look at a historical perspective on how we got to where we are. You don't have to go very far back till you see this potential gusher here, equivalent to this Texas gusher. This is Moby Dick, and he's attacking the ship Essex, which is actually the true story. A really fascinating, ironic story in which the whale, the sperm whale, actually sank a whaling ship in the Pacific, and the whalers were so terrified of cannibalism in Polynesia. They sailed against the trade winds and ended up eating each other in the lifeboats. I guess things don't always work out, but there's such a premium actually paid on high quality oil for lighting that these guys would get in these ships to collect a meager 360,000 liters of oil. It'd be 4 years, 35 men, worth about $5 million in today's budget. Very few of these people actually returned. I mean, it was pretty high-risk business. Obviously, if the whales are pissed off, you're in trouble. Today, starting with, this isn't Titusville, but Titusville in Pennsylvania in 1861 already reset the bar. In a single day, 60,000 liters could be produced from this first well. Record wells in Texas produce up to 40 million liters of oil a day. This is a stunning change in the availability of hydrocarbons, cheap fuel. Where does that lead us? Well, there's some interesting correlations. So if we're looking at across here 10,000 years ago to the present, and we're looking at billions of people, this is about 7 billion people as of today, 7.1, something like that. You see a very abrupt rise in human population. And this rather quirky statement is really actually quite frightening. There are more people living today than have died in the entirety of human history, and that's explained by the shape of this distribution. So there's more people in this peak right now than have died in the entirety of human history. And interestingly, that looks very similar to this particular plot. 10,000 years to the present, same time range. But in this particular plot, we're looking at the rise of carbon dioxide in Earth's atmosphere. So that looks very similar. Correlation and causation not always being the same thing, but it does look very suspicious. And again, you may say, well, okay, so all those people are breathing and they're respiring carbohydrates to produce CO2, and that's what the CO2 is, but it probably isn't. It's actually probably hydrocarbons being burned. This is another interesting correlation, just for you to think about. I'm not saying there's causation here, but this is GDP, gross domestic product per person, and this is the amount of energy that's utilized. So if we look at the poorest countries compared to the wealthiest countries, we see a pretty strong relationship between the amount of wealth and the amount of energy used. You can spin this two ways. You can say wealthy countries have money enough to burn a lot of energy, or you can say the availability of energy makes for wealthy countries. The availability of energy, of course, in Switzerland is very low, but the wealth is pretty high. Of course, the energy availability in Kuwait, Canada, Norway, and the US is very high, and that supports the former argument. However you want to look at that particular statistic or relationship, there is a fundamental first-order relationship between energy, food, and how we live, and that population relationship. So let's look at another time series. Here we're going back from 2000 to 1700. We're looking at billions of people. It's that same rise in population. And what we're looking at is different stages of development of that population. Now, I showed you in 1861 Titusville would be about here before oil began to be produced widely. This is certainly the Industrial Revolution supported by coal production, and this would be, I guess, biological or biogenic sustainable agriculture without that input of hydrocarbons. So billions of people correlating to the actual availability of fossil fuels. Now, how does that happen? Well, fertilizer, pesticides, obviously diesel for this monster compared to a few oats for these. This one smells better. Irrigation, less methane actually. Irrigation utilizes a lot of energy as well. In fact, the calculation is that for almost every single calorie you eat, 8 calories of hydrocarbon go into the production of that food. So 8 calories of diesel, pesticide, or fertilizer. That's what's supporting this population. It's pretty clear how tightly coupled energy and food is. An interesting experiment occurred during the Bush years, an attempt at some kind of green painting of the Bush energy policy, which was very hydrocarbon heavy, was revealed a really interesting experiment. Essentially what they decided was they were going to use methanol or ethanol from corn, and they were going to use corn as a source of fuel for vehicles. So they took corn and took it out of the food markets and put it into production of ethanol. The effects were startling. So here we're looking at commodity price of wheat, time in months, so December to February, just a few months, and wheat prices almost doubled as a response to that. And of course, this had an amazing effect outside of the US because the US, Australia, Argentina, Canada are some of the major exporting nations that other countries are dependent on those food sources for sustainability, for their survival. Immediately, destabilization, or close to, of some of the poorer countries was seen in a number of food riots. So within months of a subtle energy change, just a slight redirection of food toward energy, this sort of destabilization is seen. Very tight coupling. This slide has an interesting history. I produced it 3 years ago or 4 years ago, and it's so out of date I had to put a question mark here. And I'll show you what I originally had to say about this. And it's really a slide about something called peak oil. Peak oil is the peak of production when reserves begin to decline and we can expect to see increasing fuel prices. So the price of fuel declines through from about 2010. We probably hit peak oil about 2010, somewhere in there. And it should be declining right now, which is an interesting thing because of the two men in this picture, I would wager to say this is the more powerful and significant in the world, and it's based on that last slide I showed you. If the kingdom doesn't export 12 million barrels of oil a day, essentially our food supply is not stable. So while Barack Obama may have the most F-15s, he doesn't have possibly the most say in how the world's stability actually exists. Peak oil, though, is a really strange concept because it's technology dependent. For example, that discovery of mineral oil in Titusville was a seminal step in energy production. We are, at this moment, undergoing a similar energy revolution. And that's in the form of unconventionals, unconventional shale gas, or maybe even coal seam gas, though more controversial. So shale gas, I don't know how many people are even familiar with it. How many people in here heard the term shale gas, unconventional? Well, just about everybody. It's a profound change in our world. Just to give you an example, I'm going to show you this very complicated figure. Across this axis, we're looking at oil imports. So a country like the United States imports currently just over 50% of its fossil fuels. And on this axis, we're looking at gas imports. So currently, the United States imports about 10% of its fossil fuels. China also imports about 10% of its gas, and about the same oil. And that will rise to 2035 to be about 80%. And for the European Union, it's going to rise to over 90%. So these are importing both oil and gas. The United States, with the unconventional revolution underway, is going to be an exporter of gas by 2020. Instead of going in this direction where it's importing, needing more and more reliance on the Middle Eastern countries, it is now becoming its own animal and will actually be an exporter. Now, what's so amazing about this is that just 2 or 3 years ago, the second biggest gas field in the world was discovered. It's not in Iran, it's not in Kuwait, it's next to New York City. It's profound. This means the US will be severed from that geopolitical tension that drives so many of the world politics and tensions at the moment. But it also means that China, India, and the European Union will become more involved in that morass. So what is unconventional? What is this thing? Well, this is a conventional well. It's very complicated geologically. It has a very complex series of events that have to occur to accumulate liquid oils, trap them, mature them, and distill them so that they can be produced. It's a pretty rare bird, really. This is just brutal. An unconventional well goes to the actual organic-rich sediment, and it just drills along it, and it fractures it using very, very high-pressure water fluids, produces its own porosity, and drains the hydrocarbons straight out of the source. Doesn't have any of the migration, maturation, or complexities of geological structures that trap those fluids. It's very simple. And these sediments are very common in the world. They're very common. So suddenly, there's an enormous amount of potential energy available to us, a full step change. What does this look like? It's crazy in the US in the areas where this is being produced. A single formation in Texas where this was developed has over 10,000 wells already. 4% of these are economic. And the landscape looks like this. It's just a shotgun pattern of people putting these wells in without even knowing how the system works. It's such new technology. It's such a new idea. Nobody really understands how it works. It's just barely profitable because of investors who are believing in this idea and believing that with time it will become more efficient. And it certainly is in the US beginning to work out, but it's still only 4% of the wells pay off. And the production of the ones that don't is very poorly understood. How does this translate to Australia? Well, Australia has potentially one of the world's great stores of this, and particularly South Australia. So in Australia, there's estimated at the moment 350 trillion cubic feet of natural gas. 1.8 of those we use every year. So that's 200 years of unfettered use. That's pretty spectacular. Imagine the industries that can surround this development, and much of that is in South Australia. But there's no production in Australia. I would argue there isn't a single unconventional well in this country right now, though Santos and Beach would argue slightly differently. It's very remote to produce these wells, and they're expensive. $4 million a well. Compare that to the 10,000 wells in a single formation. In a single formation in the US. There are literally 100,000 wells in the US. We don't even have one yet. The resource is incredibly ill-defined because we don't have that well penetration. We don't have that empirical experience. So how do we best identify the prospectivity that we can afford to develop, and where do you place the initial wells? Imagine the horror of an investor that invests significant amounts of money to find a dead well. So one of the tasks we have in the Sprigg is to try and identify what conditions optimize the production of shale gas and what we're actually looking for. Where are the conditions favorable to store gas? And this is a conventional type of sandstone compared to this horror rock, which is very, very fine-grained, extremely fine-grained, so very small that the porosity is almost invisible. How do you produce hydrocarbon from this? We actually don't know how this works. So what we're doing is we're looking at examples. These are University of Adelaide students, Lisa Bruce and Sam Fraser with me in Texas, West Texas. We're looking at an exhumed or exposed in a road cut shale gas play. We look at cores that are extracted from wells, and we try to identify what the characteristic features are of the successful and the unsuccessful plays. Boy, does that sound basic, but is it ever necessary if you want to make some predictions about where you want to put those expensive wells? And boy, is it ever hard. Nobody's tried to do this before, actually, because of the technical challenges associated with this. Let me give you an example. One of our standard methods is to utilize the Australian synchrotron and the synchrotron in Switzerland, the Swiss light source, because we're trying to image something that's so very small. What you're looking at here in this image is the relationship of the actual mineral and the organic that produces that shale gas. And this is 50 nanometers. So what is a nanometer? You probably never come in contact with a nanometer. Human hair is 120,000 nanometers thick. A single molecule is 0.3 nanometers, single molecule. So we're down in that range where we're looking at things at molecular scale, almost atomic scales. Your fingernails grow at 1 nanometer a second. I thought that was cute. I found that on the web. So we're really pushing the bounds of imaging these things so we can directly understand what this process is. It's an interesting thought. We suddenly have a great deal of power. Be careful of what you ask for. Peak oil is gone. We have an unlimited amount of hydrocarbon available to us. What are the implications of that? Well, these are the implications. Fossil fuel reserves, oops, boy, I really have a problem with this, are 4,000 to 6,000 gigatons. It really doesn't matter what these numbers are, but 4,000 to 6,000. The present atmosphere is 760 gigatons. So just divide this, one of these numbers, the range, by 760, and you get 7 times pre-industrial CO2. So we're arguing right now about 1.5 times. We're at 380 ppm, according to our Picaro instrument, when you guys walked in. We're talking about thousands of ppm in the atmosphere. And this is just a quirky number, 125 kilograms of CO2 you produce every time you fill your tank on your vehicle. So 7 times pre-industrial CO2 is what we could potentially produce with our newfound wealth. That's a pretty scary number. But there are some good reasons to go to this new unconventional source, because gas is arguably cleaner. It's possibly 50% cleaner than coal. There's issues about aquifer contamination. Certainly in coal seam gas, there are issues that I think about. In shale gas, like we have in South Australia, these are not issues. The actual resource is very, very deep, far deeper than the aquifer, and decent drilling management will remediate this problem or eliminate it entirely. I sound like I work for Exxon. There is this issue of water use during fracking, which is millions of gallons in Central Australia and South Australia. That could be quite a problem. And then there's this thing, fugitive emissions. Now, this has blown up in the last year. We anticipated it. We knew it was coming, but it's really hit the media. And we've seen a lot of articles like this. This I saw in the Australian anyway, future carbon tax liabilities of up to $4 billion a year in Australia alone if fugitive emissions of methane from unconventional gas production turn out to be substantially higher than expected. Boy, does that cool investors. And does that slow the industry down? Now, we just have been given all this power, all this energy, all this potential wealth, if you believe one of those relationships. And now, it doesn't look like it comes completely free. But the thing is, we don't know. We don't know what the fugitive emissions are. Nobody's measured them. Nobody's had the capacity to actually go into the field and discriminate background methane, which is about 2 parts per million, versus 4 parts per million, which would be a leaking well. But this machine can do this. And at the University of Adelaide, we believe we'll have the first program in the world that will actually go and investigate this question and determine exactly what that number is. Are we dealing with something that is lethal, or are we dealing with something that is manageable, reasonable, and on a similar scale to any methane-producing activity like agriculture, industry, or swamps? We don't know, but we can with this instrument. So what you've been doing since you've been here, we've been monitoring you, and we've been seeing how much carbon tax we're going to charge you before you leave this room. And if I can work out how to do this, all right, let me show you what we're doing. So currently in this room, I told you the background is outside the room, in the outside in the real world. It's 380 parts per million. You are at 716 parts per million CO2. The levels of CO2 in this room are already equivalent to the Cretaceous, one of the hottest times in Earth history. And I'm wearing this jacket and I'm pretty warm, but you're recycling a lot of air, 724 parts per million CO2, so almost double what it should be. And that will probably rise through the presentation. The amount of methane is 1.8. That's not too dissimilar to background, and methane is here, and you can see that drop and then the rise. That drop was when Mike Hatch, where's Mike? Mike, who is running this device and helped set it up. Mike took that intake and he ran it outside to get a baseline. And when you came in, you increased the level by about 0.5 ppm. So what that tells us is this is the baseline and this is your effect. We need to know that in shale gas fields as well. We need to know before they drill what the actual baseline measurement is, because there are all kinds of natural sources of methane. And this instrument will tell us that if we can get there before they actually drill. Now, the concentration of CO2, that's the background outside before you came in. And you're sitting pretty constant. CO2 is being taken out by the air conditioner, so we're kind of at equilibrium here. So we can do that. We can also look at the isotopic composition, which is even more remarkable. And we could see that the CO2 outside, is that CO2 or methane? Yeah, CO2, has a different isotopic composition than in this room. So you're probably more vegetarian than the average outside car-burning population, which makes sense because you're at a carbon talk. Not to stick to any stereotypes. Oh, sorry. Okay, getting back to the point. So that's what this wonderful instrument is, and it was supported by the University of Adelaide with funds that they found in very tight times because they see that this is an important direction to go in. So what we can do is we can go to these places. This is a shale gas field, or a CSG field in Queensland, and we can monitor the different sources, and we could back out how much of that CSG is actually coming from the fracking operations, from the actual unconventional production, versus how much is natural. So we can determine a number to tax these people, but more importantly, we know whether we're dealing with something that's really threatening or is a tempest in a teapot. How does this work? How does CO2 actually change the atmosphere? That's the next question. What do we have to worry about? Is this really concerning? There's certainly a discussion that climate isn't changing, or that if climate is changing, it's not anthropogenic. But there's a very strong scientific consensus that it is changing and it is anthropogenic. And I'm going to show you my take on that. My take is flavored by the geological record, which is a far more scary thing to see than the actual measurements of instantaneous change that we have today. This is a very depressed Swede who went into his house in winter and calculated in 1896 the effect of CO2 on climate, and he thought it was a good thing. Of course, if you're in a dark Swedish winter, you would. And he actually came out with a spectacular number that, 5 degrees C temperature change should result. By the end of the winter, he calculated 5-degree temperature change associated with anthropogenic CO2, which is amazing because the supercomputers we have today are calculating 4.5 degrees. So it's really pretty impressive. But the point of this really is CO2 directly doesn't do that much. CO2 itself, the physics of the CO2 molecule in the atmosphere, don't do very much. It only will change directly temperature 1 degree C. The importance of CO2 is it's our thermostat. It actually regulates the planet temperature changing functions. I'm going to show you what that means. That's total gobbledygook, but I will show you what that means, and you will see why it matters what CO2 is and how it changes. Work with me here. There we go. Okay, so one way you can think about this, and this is how the media presents it to you, is that as this is CO2 rising from 1880, pre-industrial, to 2000 or a bit past, CO2 is this line here. It's rising from 280 to where we are now at 380. And this is a temperature average from various sources. You can argue about it, but it's kind of probably pretty accurate. And the idea is that one increment of CO2 gives you one increment of temperature change. That's a linear change. And this is just not what's happening in the geologic record, at least. When we go back and we look at our high-resolution climate records, where we get most of our information about how climate changes, and this is an ice core record, drilling an ice core in, this is Greenland. Each one of these layers is an annual cycle, season, and we can look at the bubbles and the composition within those and then capture an air sample. And within that air sample, we know how much methane, how much CO2, and what the isotopic compositions are, what the temperatures over the ice were. And we get this wild ride. I mean, this is like a roller coaster gone crazy. This is 110,000 years ago to zero, to present. And look at this crazy climate. That is not indicative of linear change. This is not stable, nice, oscillatory change. This is a dramatic, very variable system. And we live in this nice little, strangely homogeneous, stable period. Now, how does this work? Well, our sister planets, Venus and Mars, have similar compositions to us, very similar, in fact. But they're not very habitable. Maybe Mars was once, but it certainly isn't now. All of its greenhouse, all its CO2 is actually frozen at the poles because its average temperature is below the freezing point of CO2, which means it's got dry ice glaciers. Spectacular. Venus has all of its CO2 in its atmosphere. It's boiling. It's 900 to 800 degrees on the surface. Fantastically hot because of this high greenhouse and heavy atmospheric pressure. The Earth cycles its CO2 between its oceans, its atmosphere, and its rock record. And that's why it's habitable. It has one of these things. It's got a thermostat, a temperature-regulated thermostat. Okay, so how does it work? Well, this is out of a car. This would be out of my first car when I was a teenager. And most of the time it didn't work. But, and any of you who remember the Devil's Elbow and all the cars strewn up to Eagle on the Hill, well, they all had this, right? So this pattern of thermostat has been replaced by electronics now that work a lot better. But essentially what happens is there is a piece of plastic or paraffin, actually in the old ones, paraffin that is temperature sensitive. And it becomes stickier, more resistant as it cools, and it allows the spring to slam it shut. So it stays shut, and it prevents any cold water from getting into the engine block. And in this system where the heat actually builds up on the paraffin and becomes stickier, the spring opens the slide, and the valve allows cool water in, and the engine cools that way. So the Earth has a thermostat, and that's why it's habitable. It regulates CO2 between the oceans and the atmosphere, much like your car does. And that thermostat is really complicated, but it's very active and very important. So CO2 is constantly coming out of volcanoes, and if nothing happened to it, we would look like Venus very quickly. So CO2 is coming out, and it's being sucked up by plant matter, material that grows. It's being absorbed in the oceans. It's going into any number of different sinks at different rates. For example, it's utilized to weather silicate rocks. These are just regular old rocks on the surface. And it takes that CO2 out of the atmosphere, and it buries it into sediments. Okay, and the warmer it gets, the faster this reaction goes, and the more CO2 gets drawn out of the atmosphere, the faster the reaction goes, and the cooler the planet gets. That's how brilliant this system is. Well, there's another equivalent feedback with organic matter, and there are a variety of others. So what that leads to, rather than this pattern, is it leads to this wild spiky pattern because those feedbacks are pretty clunky. They don't work all that well on very short time scales. They're not fluid. They're not nice and smooth. Imagine if your thermostat in your car was like mine when I was a teenager. This opened about every 5th time it needed to. So the car was either overboiling or it was spewing all kinds of fuel out the back because it was too cold, but it never worked properly. Well, that's kind of on the resolution that we would like it, how the Earth system works. Not so good. And let me show you why. Here's an example of a feedback. Albedo. This is 18,000 years ago during the glacial maximum, and this is the ice cover in the northern hemisphere. It's a huge white area that's reflecting sun back off the planet. and it's really keeping the planet very cool. This is today. Much, much less white material, much less ice at the higher latitude. And as this disappears, there's less light reflected and the Earth warms more and it melts more of the ice. More ice disappears. And the Earth warms more and more ice disappears. It's positive feedback toward warming. It's throwing us out of an ice age and into a greenhouse or warm period because this very important area of reflectance is disappearing. This is the alternative. This is something else we study. This is a runaway where the ice has covered the Earth. And it started at higher latitude and it overwhelmed the CO2 effect and reflected more and more sunlight until the planet became so cold, it is thought that maybe life was extinguished during this period of time, and it subsequently recovered. It's research work that's occurring in the Sprigg as well. There's a long list of feedbacks. They're complicated, they're hard to quantify. At least this, our ability to predict the future climate is dependent on our knowledge of past climate. Part of this is if I hadn't seen it, I wouldn't have believed it. I'd never believe a snowball Earth. I'd never believe it was possible. I could never imagine it as a modeler. But we have geologic evidence, mostly coming from South Australia, actually, very famous internationally. The feedback systems controlling the Earth's temperature are far from understood, far from understood. In fact, we're just even now identifying the relevant feedbacks, just trying to understand the processes that are critical. What we are aware of is that the climate works in two ways. There are modes in which there's a warm and a cold condition, a greenhouse and an ice house. We're in an ice house now, but most of Earth's history, actually, if you look at this table back to 2.3 billion years, these are ice periods. The majority of the time is actually greenhouse, hot time. That's the really stable period, stable climate system. And we know that as we look at our Picaro and we make measurements outside and we look at ppm of CO2 and we climb towards 700, remember the room right now, it's 735 ppm. As we climb toward that number, we're returning every year, 1 million years toward that hothouse, that greenhouse period of the Cretaceous. 1 year, we're going back 1 million years in CO2 concentrations and records of CO2. So we're actually now in the Pliocene, 3 million years ago. What was the condition of the Pliocene? There was no ice sheets on the northern hemisphere. It was a very warm period. It was demonstrably unsustainable for our present civilization. But we're not going to stop there. We're on a trajectory to head much further along. The Cretaceous, even the Pliocene, extraordinarily warm. Crocodiles in the Arctic. The oceans, for much of the time, were warm enough not to have significant animal life in them. No glaciers or ice caps, very high sea level steads, and of course, Canberra, escaping as always. Those politicians. So some of you may have heard of the IPCC. The IPCC is tasked to try and understand and give us an estimate of what these changes are. And for those of you who are into conspiracy theories, thinking climate scientists are benefiting and driving Cadillacs and limousines, all I can say is that the number of people involved in an IPCC report are over 200 for AR4, the last IPCC report in 2007, there were at least 200 climate scientists involved. And given that the total funding in the US for paleoclimate research was about $6 million, if you divide those 200 people by that money, it doesn't come out to much. So there really isn't a conspiracy, and this really is a sincere effort at trying to synthesize and bring about some kind of understanding of climate. But I will argue that this is so conservative that it is scary when you actually contemplate what could be wrong with this information. Okay, so how do they do this? How did they get to the IPCC 4 degrees, 2 to 4 degree temperature range by 2050? Well, first they begin by estimating how much CO2 we're going to produce. So those are economic models. So these are different scenarios in how fast India grows, how much CO2, how much hydrocarbon China will utilize. And then they take these processes and they use these supercomputers they've got in Boulder, Colorado. Man, they're big and powerful, and this is what they look like. And they take pixels of the Earth and they model the physics within those pixels using the processes that they can quantify. Now that's the key thing here. They use the processes they can quantify, the things they measured, that they know the numbers for, that they can put into the model, because if they put estimates in, the model blows out and they get crazy numbers. So they have to know what the process is, and they have to be able to quantify it. And if they don't include it. Well, I would argue that most of the greenhouse condition we're moving toward, we don't know anything about. We don't know how it works, and we certainly haven't quantified it. And they would argue the same. And what they would say is, we can't put it into the model. And I would say, well, if you don't put it in the model, what are we talking about? We're talking about a complete miscalculation of what climate can potentially do. Let me give you an example. It kind of matters how fast sea level will rise. The IPCC estimate is pretty modest, 0.24 meters, 24 centimeters by the end of the century. 24 centimeters, according to these various scenarios they produce, not terribly a lot of sea level rise. I wouldn't be too worried about it, but they do qualify it here. There's this small caveat, model-based range, excluding future rapid dynamical change in ice flow. Well, that's never captured CNN's attention, but when I read that, it frightened the pants off of me, because this is the only thing that matters. Let me show you why. As a geologist, we look at the geological record and we get a sense of what has happened. We know what can happen. We don't always know why, but we at least have a historical record of what happens. And this is simple. Let's say we have some coral reefs. Coral reefs grow up to sea level, and if we date the coral, 14,310, we know the sea level was at least that high. If we have a coral at 14,650, we know sea level was that high. And the difference here tells us how fast that sea level rise as a minimum was possible. Well, that minimum was closer to 22 meters in 350 years. That's 40 millimeters per year. IPCC is saying 24 centimeters in 100 years. We know this is possible. We see it in the geologic record. 120,000 years ago, when CO2 was at the present level, sea level was 6 meters higher. That would flood Manhattan, and this is what Australia looked like. Spectacular. Great boating opportunities, much improved. We could have ferries to Alice Springs. I think this is great. In fact, we only need to kind of dig a ditch, I understand, through Port Augusta, which is kind of a ditch, and we could actually do that already. So how does this happen? How do we go from these incredibly conservative numbers to something that makes me worry, at least? Well, imagine 5 or 6 years ago, even go back 10 years, we imagined the Greenland ice sheet was inviolate. Its top is 3,000 meters high. It's so high latitude, it's so cold there, it's hard to imagine. You can't imagine meltwater lakes forming on the top of the Greenland ice sheet, can you? It's just crazy. But of course they do, and we know that from satellites now. We didn't really pay attention 10 years ago even. And since then, we've become aware that the Greenland ice sheet in summer spectacularly forms cracks. These meltwater lakes pour down the cracks, and the whole ice sheet lifts up and begins to float toward the ocean. It floats on its base. It actually is measurable. It moves up almost a meter, and it floats and it slides. The sense of this is, instead of melting downward, as we always thought would happen, glaciologists being we. I'm not a glaciologist, so I'm not responsible here, but we always assumed that melting would occur from the top down. But in fact, the Greenland ice sheet is capable of actually sliding into the Atlantic Ocean and melting. And that is when we see these huge shifts in sea level change. That is when we see meters per years or decades. So that is something we've learned in the recent that tells us the IPCC conservative is a minimum. So how fast can these processes occur? Do we have to worry about them? Do our kids? If they do, well, maybe the kids deserve it. I don't know. They're kind of spoiled. They got an attitude. But anyway, so let's say we're going back to our annual our annual seasonal record of ice, and we measure our temperature changes and our CO2 fluctuations, and we get to something called this enigmatic younger Dryas period, and we see this really large shift. I think, there we go. Oh, I guess that was so you'd pay attention. This is animation, I guess, at its worst. 12 degrees C. 12 degrees C in 3 years. 12 degrees C in this region in 3 years. And that is calibrated based on counting each one of these layers. 12 degrees, a spectacular amount of change. That's how fast this process can happen. Now, maybe you don't worry about it. It really depends on how much our civilization can sustain in terms of temperature change. But we live here, and civilization solely exists here. Strangely enough, there weren't big farms in West Texas during this period of time, because the climate and the ice sheets were moving so rapidly back and forth, there wasn't an opportunity. You just kind of had to run ahead of them, then run back up north and stay ahead. But during this period of time, this strangely anomalous part of this 110,000-year record, there's a stability, and that's where civilization evolved. Boy, I don't want to leave that plateau. I want to just stay there, whatever it takes. And I'm back to this thermostat thing. Whatever that thermostat is, it's keeping us there, and I don't want to muck with it. Those civilizations that have developed very efficiently, like the Mayans, when we look at climate records, and now this is going back to 2,000 years, a 9-year drought in the Mayan civilization is attributed to the collapse of this very, very complex culture simply because they didn't have the wherewithal, simply because they were so efficient, built out to the very margins of their sustainability that they couldn't actually survive those drought years. So where do we look if we want to understand the Earth's climate? Our future mean state, our future average, is going to look a lot like a greenhouse period because that's what we're seeing in terms of CO2. It's really important then how we get there, and it's most likely we're going to see tipping points and thresholds. That's as these feedback processes kick in and positively reinforce each other and drive us to that new climate state. When does the ball move to that new stable position? When is that going to happen? When it happens, is it going to happen in 3 years, 10 years, 15? That's what the geologic record suggests to us. IPCC is painting us a very, very conservative, simple picture of this process. This is an important point, and if you hear one thing in this lecture, this is it. Tipping points occur when we strongly force a system. And for all those climate skeptics out there, I would argue this one thing. There isn't a period in geologic time when a systematic mechanism of oxidation of all of the reduced hydrocarbon reservoir was possible. We are unique in history of the Earth. We have a capacity to do something that's not been seen before, and we are doing it with abandon, incredible efficiency. There is only one time that I am aware of when 1% CO2 rise per year ever occurred, and that you have to go back to 635 million years ago. And this is a period that triggered one of the most catastrophic feedbacks that may be active in our system today that we have not yet seen, and that is methane hydrates. Methane hydrates are a huge unknown in our climate system. We see them active in the geologic record. We see them driving climate to that new state. They are maybe the mechanism that is responsible for that spiky climate behavior I illustrated in that isotope record from Greenland. And they are ubiquitous around our margins. They occur on all our continental margins. These are frozen greenhouse gases, and they have profound efficiency, 23 to 110 times the CO2. This is how much gas hydrate there is. This is how much fossil fuel. So we did our best and burned all that stuff up. This is twice as large and that much more efficient. This is our bugaboo, at least one. We actively work on this problem in the Sprigg. We try to understand it in the geologic past. And we have found it is responsible for one of the greatest climate changes in Earth history. And it's actually spectacularly recorded down by Hallett Cove. There's some spectacular seeps, methane seeps from 600 million years ago there. Chris Vandenborsch from Flinders with one of my students were working on those. Frighteningly, we see this record beginning to exhibit itself in the North Atlantic off Svalbard, Spitsbergen. These are records, geophysical records from a cruise that show destabilization of these methane clathrates as the ocean warms, as these methane ices begin to warm, they melt and they release methane to the atmosphere. We're talking again about that positive reinforcement. Once that process starts at high latitudes in terrestrial permafrost, that methane warms the atmosphere, more ice melts, more methane clathrate melts, more oceans warm, more clathrates melt, and more warm until the entire reservoir zippers open. That's a threshold we don't want to explore because that is a point of no return. I don't know where it is, but I certainly would like to know where it is. I think this is my last slide. I had initially the Dummy's Guide to Civilization, but I didn't want to, I really picked that off of a bookstore. You know, it was really not to be patronizing. But I just think there are some really important things here. Our present requires energy. We need the energy to feed our people. We need it for stabilization. Do we currently know enough about our climate system to actually manage it? We're talking about carbon taxes or this and that. Do we actually know how to manage our climate system? We don't even know what the feedbacks are. When we couple these problems to our most efficient means of solving problems, economic reward, I believe we will be on the way to resolving the climate issue and the sustainability issue. Until a company can make a buck out of doing this and solving this problem, I don't think we're going to get anywhere. So in some sense, I see the carbon tax as one of the most profound pieces of legislation that will free us and make our children safe. But on the other hand, boy, I wish it were done better. And boy, I wish we understood more about the science, that we knew where those thresholds were. So I think that's the last slide. I mean, I guess this talk is really about the balance between this wonderful discovery, this new frontier we have, this new energy source, and the new power we have to do damage to ourselves, and how are we going to balance and stabilize those things. So I'll leave it there.